you make sure you get the recorder started, because this is the portion where things can be interesting, and we need to make sure it's recorded. So start it. Right. Okay. So when you read the notes, okay, if you read this part here, and by the way, I fixed the one thing in Moodle that stopped displaying all the notes. So it's now all fixed. Everything should display just fine now. So when you read the notes here, it does contain the algorithm already. Okay, so this is the algorithm, and the indentation is not right. It is actually missing the indentation. But this symbol here, okay, the symbol that looks like a square bracket, except the top is open, is called a floor symbol. Okay, the floor symbol means we are taking the integer that is less than or equal to whatever is inside. Okay, that's the one thing that we haven't really talked about in the previous class. What do you think is the floor of 2? We are looking for the largest integer that is less than or equal to 2. It's 2 itself. Okay, very good. What about 3.5? 3. How about 3.9? It's still 3 because we're looking for an integer, the largest integer that is less than or equal to 3.9. Now here comes a tricky one. What about negative 0.5? The largest integer that is less than or equal to negative 0.5. Negative 1, not 0. So we're not rounding, in a way. We are always, going to the integer that is less than or equal to the number, the largest integer that is less than or equal to. So in this case, we're just using that operator to pick one of the 2 indexes when you have an even number of elements in the array. Because let's say you have 4 elements in the array, okay? If you have 4 elements, and this is the first iteration, B starts with a value of 0, E starts with a value of 3 because 3 is the index of the last element in the array. 0 plus 3 is 3. 3 divided by 2 is 1.5. 1.5 is not a valid index because in order to use a number as an index, it has to be an integer from 0 to bar a bar minus 1. So when you have an integer 1.5, it doesn't really work because it's not a valid index. So using the floor operator, we basically just bump it down to 1 in this case, so it becomes a valid index. Now we could have used the other types of operators too. One is called the ceiling. The ceiling function returns the least integer that is greater than or equal to the integer. So it basically is just the opposite. That works too. We can also use the regular rounding function, which means any value that is greater than 0.5 rounds up, anything less than 0.5 rounds down. So they all work. In fact, it can be even random. Okay, sometimes you round up, sometimes it rounds down. It will still work. Binary search works, regardless how you pick one of the 2 middle elements. You can pick one or the other, and it still works. Okay. But in this class, we use the floor function simply because that's how C will operate when you have a division that has a fractional part. All right. So are there any questions about this operator, the floor operator? No questions about the floor operator? Okay. So what I'll do next is I'm going to trace this algorithm, just a few times, so that we are kind of familiar with the expected behavior. Yep.
What about with the square brackets? That's just for the array, though, for the M.
You mean this part here?
Yeah.
Well, let me put this into a spreadsheet. As I trace it, then you can go ahead and ask questions. Okay, because we're gonna have to do that anyway. So here we go. Let's get started with new spreadsheet. There we go. All right. And I think I remember the algorithm well enough that I don't really need to read my own notes. The floor of B plus E divided by 2. If A bracket I is less, M is less than the key, the value that we are looking for, then we'll do one thing, else, not just else, it has to be else if A bracket M is greater than K, then we do something else, and if until one of 2 things is true, one is A bracket M equals K, which means we just found an element in the array that matches the value that we're looking for, or B is greater than E, because B is supposed to be the index of the first element that can still contain, that can still have the value of K. E is supposed to be the index of the last element that can still contain the value of K. If B is greater than E, that means there's no element left, because there's no number between B and E, because all the indexes of elements that are supposed to be, that can still contain K, all of those indexes should be larger than or equal to B and less than or equal to E. So when B is greater than E, then there's no element left in the array that can potentially have the value of K. Is that okay? Okay, that's what we kind of talked about on Tuesday. Okay, so what I have done here is I'm missing 2 lines, and let me see if you guys still remember how to work out these 2 lines. Assuming the array is sorted in a non-decreasing order. Non-decreasing order is kind of like increasing, except in this case I can have duplicate values. I can have 2 values of exactly the same next to each other. Okay, so if the array is sorted like that, and I already know that A bracket M is less than K, which part of the array can I eliminate as possible, possible range that can still contain the value K? The first part or the second part?
You can reduce the second part.
If A bracket M is less than K, it implies that A bracket M minus 1 is less than K because it is sorted in that way. So that means I can throw away everything at index M and also before. Okay? So which one should I be moving? Should I be moving B, which is the index of the first element that can have the value K, or should I be moving E, which is the index of the last element that can contain the value K?
B.
B, okay, so we have a B gets something here. I'm gonna leave it blank just for the time being. So the other one has to be moving the other part, moving E instead of B. So the question now is, how am I going to update B? The most intuitive answer is just M, okay? We just found an element and compare to it and understand that, hey, everything before A bracket M, the element A bracket M, has to be less than K. But we're forgetting one little thing. Go ahead.
Yeah, I mean, put down what's in bar A bar in terms of how many elements.
Say again?
How do we know what's in bar A bar?
When I give you the starting condition of the trace, I will give you the number of elements.
When did you do that?
I haven't done it yet for this one. For this example, I haven't done it yet.
Okay.
But for your homework, there is an initialized array with a known number of elements.
Okay, sorry.
Yeah, that's okay. Okay, so what we're forgetting here is A bracket M itself is also less than K, and therefore M cannot be the index of the first element that may contain K. It has to be M plus 1. Exactly. Okay? And for the same reason, this one cannot be E, because we already know that A bracket E is an element. We already know that A bracket M is an element that is greater than K, so it cannot be the index of the last element that can still contain the value K. It has to be E minus 1, because it has to be the one, M minus 1, the one before index M. Okay, so the plus 1 and the minus 1 seems pretty minor. Is it going to affect the algorithm all that much? Well, it does. Okay, that's basically the whole basis of your homework assignment. Okay, so I would first, trade this. Oops, I just erased my own right in here. Okay, so here I'm going to give them line numbers, and we'll trace this twice. Okay, we'll just have 2 test cases for this one, and we'll trace it and figure out, okay, how does it work when it is supposed to be correct. Okay, so this is the correct version. We'll trace it twice. We definitely have comments because we have line 10, line 5, and also line 7 having conditions to evaluate. In fact, comments needs to be a little bit longer in this case, at least that one. We have line number. We have B, E, K, M, and then we have K, and then we have the array A. In this case, I'll just go ahead and make it like 4 elements. So we have a bracket 0, bracket 1, bracket 2, and also bracket 3. And the only requirement is they have to be sorted in a non-decreasing way. Because if my algorithm is assuming the array is sorted in a non-decreasing order, and yet the array itself is sorted in a non-increasing order, then the algorithm is not going to work because the assumption is not there. So we'll go ahead and just put some kind of random values here, and then we'll look for a particular value. But before we do that, let me make everything a little bit smaller so I can see all the columns at the same time. No? That's nice. Okay. B can start with an unknown value. E can start with an unknown value. M can also start with an unknown value because they will all get initialized before they get used. K, on the other hand, has to be initialized because it is representing what value are we looking for in the array. So which one do you guys want to try? Okay, it doesn't have to be something here. It can be like something tricky that is not here, at one end or the other end or right in the middle. Go ahead, give me a suggestion. Think of the most tricky case in this particular example. 0. Okay, we'll try 0 for this test case. Okay, 0 is here, and then we start with line 1. B gets initialized to 0. On line 2, E gets initialized to 3 because it's bar A bar minus 1. Don't forget the minus 1. We don't track line 3 because it is just a line to indicate the beginning of a post-checking loop. We go straight to line 4. What do you think is M in this case? It's 1, exactly. Okay, because it is 0 plus 3, which is 3. 3 divided by 2 is 1.5. The floor of 1.5 is the largest integer that is less than or equal to 1.5, which is 1 in this case. Very good. We go to line 5. We have to indicate the result of this comparison. A bracket M is A bracket 1 because M has a value of 1. It has a value of 2. We're comparing that to 0. 2 is less than 0 is false. Okay, so that means we have to go to line 7. Okay, we have to test the second condition. This is a multi-branch conditional statement. A bracket M is greater than K is true. Okay, because 2 is greater than 0 is true. Then we go to line 8, which is the branch corresponding to the condition of line 7. Line 8 is just going to update the value of E using M minus 1. M is 1 already. 1 minus 1 is 0. So I have now 0 in E. Okay. And then we move on to line 10. Now let me just kind of pause right here and kind of talk about what does it mean when B and E are the same. Okay, it is still okay because if I tell you the index of the first element that can contain the value K is 0, and the index of the last element that can contain the value K is also 0, what does that mean? Is there a range of number that meets that criteria, starting with 0 and ending with 0? Yes. Which number is that? 0 itself. So that means I have one element left that may contain the value 0. Okay. All right, so we go to line 10. A bracket M is A bracket 1 because M still has a value of 1 at this point, which has A bracket M has a value of 2. 2 equals to 0, which is in K, is false. Even with short-circuited evaluation, I have to move on to the second one because this is false, but because it's a disjunction, I have a second chance to make the entire expression true. So now I have to evaluate the second one. Or B is greater than E. B has a value of 0. E has a value of 0. 0 is greater than 0 is false. So now we have false or false, which is false. And what do you do when the until condition is false? Well, we have to go back to the beginning. Okay, so we'll indicate the answer is false here. Then we go back to line 4, which is going to update the value of M. In this case, M is going to be easy. B is 0, E is 0. 0 plus 0 is 0. 0 divided by 2 is 0. The floor of 0 is also 0.
zeros.
Hmm?
I should say it's a lot of zeros.
Yep. And now we move on to line 5. We perform the first comparison. A bracket m is a bracket zeros because m is 0, has a value of 2. 2 is less than k, k has a value of 0, is false. And then we move on to line 7. A bracket m, which has a value of 2. 2 is greater than 0, which is k. Sorry, I should change the other one too. That's true, right? 2 is greater than 0 is true. This one I have to change it back to k because we always copy the expression itself and not the value of the variable. Okay. And then we have to go to line 8 again. Line 8 is going to change e, and this time how are we changing e?
-1.
-1. That's right. Then we go to line 10. Line 10 has two conditions, potentially two conditions to evaluate. A bracket m is a bracket 0, has a value of 2. 2 equals to k, which is 0, is false. Okay, so that means we have to evaluate the second condition. B is 0, E is -1, B is greater than E is true, so the whole expression is true, and it is time for me to exit. And that's it. It got out of the loop, and a bracket m does not equal to k, and that's the indicator that we could not find a value in the array that matches the value that we're looking for. Okay. Are there any questions about this particular trace? Any questions? All right. If there are no questions, I'm going to start on the second trace. Okay, so I'm going to copy this entire thing and paste it into the next sheet here. Erase everything, and now we look for a different value. Let's try to look for a value that is in the array, but is at a spot that is not easy to find. Okay, which one do you think is not easy to find?
5.
5 is easy. 5 is the first one, so we will locate it pretty much in the first iteration.
Yeah, but it's gonna locate. There's gonna be a problem if we run 5 because there's no case where the k we choose.
Okay, how do you want to initialize k? What value should we look for?
No, I was looking at k being 5.
K is being 5? Okay. K being 5 is going to be a really easy case because that's the first one we compare to. Okay, let's go ahead and track it down. On line 1, B gets initialized to 0. On line 2, E gets initialized to 3. That's the same as last time. So is the first time we do line 4, okay, because M is still getting 0 plus 3 divided by 2 and the floor of that, which is 1. And then on line 5, we compare the numbers. So this time we have a bracket m, which is a bracket 1. It has a value of 5 already. And we ask, is 5 less than k, which also has a value of 5. 5 is less than 5 is false. Okay, no problem. We get to line 7. And then we ask a similar question. A bracket m, once again, is a bracket 1, which has a value of 5. 5 is greater than k, which is also 5, is false. Okay, that's fine. Okay, that is not a problem. We are now done with the multi-branch conditional statement, starting on line 5 and ending on line 9. Okay, we did not end up changing B or E at all, but that's fine. That's not a problem. We get to line 10 here. Line 10 has to evaluate a disjunction. Excuse me. A bracket m equals k is true because a bracket m is a bracket 1, which has a value of 5. K has a value of 5. 5 equals 5 is true. And because we are using short-circuited evaluation, I don't even bother to look at B and E because the expression has to be true already, knowing the left-hand side of a disjunction is true. Okay? And because the condition is true, I'm getting out of the loop. I'm done. One iteration. Okay. Any questions about this particular trace? No questions? All right.
Wait until we do our own.
Yeah, well, the homework is a little bit different. Okay, so are there any other, do you guys want to trace this anymore, or do you want to like move on to the homework?
Is this the one, which one is the one where we do this going by, like if there's if there's like 5 elements in the array, we would check the first element, and then we'll check the third, and then just like you're cutting everything in half, binary search.
This is binary search.
So then,
This is binary search. It is the algorithm that we derived in the previous class. It's also in the notes too. Yep.
So what would be a tricky number for this one? You said you asked for us to pick one that
Right.
would be tricky. What would be a tricky one?
Well, I would say a tricky one would be 10. 10 is going to be, because we only have 4 elements. I think 11 is the tricky one, because 11 would take the most number of iterations to get to it. The first iteration, in this case, will, if I look for 11, the first iteration will eliminate 2 and 5, because I'm picking index 1 to compare to. That remains, what remains would be the element at index 2 and index 3. Out of those 2, the first one I will pick to compare is actually 2, because 2 plus 3 is 5. 5 divided by 2 is 2.5. The floor of 2.5 is 2. So I would compare to element 2 first, confirm that is not what we want, and then we only have 1 left, and that will be the time when we actually find it. So it will take the third iteration to confirm that 11 is in the array. Okay. And that's a good exercise. I mean, I just told you the answer, but it doesn't hurt that if you go ahead and trace the algorithm, change k to 11, and see that it takes 3 iterations to confirm that 11 is in the array. Okay, because that really helps you to kind of understand how it is supposed to work when the algorithm is correct. What do you mean by when the algorithm is correct? Well, let's take a look at the homework assignment. The homework assignment is already here, and you just go to array 2, because this is the second homework assignment related to arrays, and here's the file. I'm going to save link as, make sure that I can find it. Sorry?
isn't it array 1? No?
Array 1
Yeah,
was
array
due,
one.
is due today, and
Was
we'll go over that too.
Okay.
So now we have array 2, and the title or the name of the file kind of gives you an idea of what it is about. It is bad binary search. Okay? And you look at the algorithm, and you say, hey, that looks almost exactly the same as the other one.
Oh, no, +1.
Yeah, it's only missing the +1 here and the -1 over here. So it doesn't seem like it's going to be that bad, right? I mean, it's just missing 1. Well, I give you 3 cases to trace. Okay, this is the first, second, and third test cases. So each one you have to basically start from the beginning and run it all the way through until it ends. And you will find that missing 1 is more than enough to make the algorithm go cuckoo and not be able to finish in some cases.
And get a
Okay?
zero.
Sorry?
And get a 0
Get a 0?
for homework.
No, your homework, your job, your job is to, do the trace, and if you think the trace will not end, meaning the algorithm will not complete, indicate that is the case, and tell me why you think it is not going to finish. And the most typical explanation why you think a loop is not going to finish is you do not see any changes of the variables whatsoever within one iteration. Okay, because if the values of the variables is not changing within one iteration, it's not going to do it in the next iteration, and therefore it will never end. Exactly. So that's a very good explanation why it is an infinite loop. Okay. All right. So this is your homework assignment for the next 7 days. I don't think it will take that long to finish it, but that's your homework assignment. And this time, remember, the algorithm in the homework assignment is incorrect. I just want you guys to see, when the algorithm is incorrect, what's going to happen.
So for indicating that it would, you just want that at like a comment line?
Yeah, just write it on in the cell, like the cell right below the line where you think, oh, okay, I think I can see that this is not going to end. Just write it down there, and it's fine. Okay. Are there any questions about the homework assignment? Any questions about the homework assignment? Are there any questions about binary search in general? Or time complexity? Remember the stuff that we talked about last time? No. Nobody remembers anything about PAT.
Pass the roll sheet around, Professor.
Okay, I will do that. Okay, so I'm gonna pass the row sheet. Well, in that cartoon, that I showed you the other day, it was okay. Let me show you the cartoon again. It's
Non-deterministic and polynomial time.
right. But the student is saying, I just wanted to learn how to program video games, and I think these days, it also applies to apps. Okay, if you're writing program for mobile devices, because there's a huge market of mobile app development or developers. A lot of people have good ideas. They want to do something with the mobile device, but they don't know how to program it. So they have to rely on developers, programmers who know how to program, mobile devices. But even so, even with a mobile device, understanding, the basic foundation of programming is actually important. Okay, it is actually very important. All right. And I think we already talked about the importance of video game programming and how how a good understanding of computer science concepts, especially abstract concepts, is going to be important. I'm going back to this class now, and let's see. This is the PM class. So we are basically moving on at this point. I'm going to move on. Let me change the highlight because I kind of messed up the ordering of the topics at this point. So I'm going to have to use the highlight to show you where we are at this point. We are not in topic 5. I will save topic 5 for later. And we are actually in topic 6. I messed up the ordering, but I'm using the highlight here to help remind us, where we are at. Okay, let me ask you another question first before we get into subroutines. When I explained how an algorithm is derived, okay, using all those steps, keep revising the same thing over and over again, each time only adding a little bit of new stuff to it or make a little bit of clarification. Was that explanation helpful? I mean, are you guys getting anything out of it? I cannot test you, okay, so you don't have to worry that I'll test you, with that process. But what I'm asking is, is that does it make sense to you that you're gonna go step by step, just add a little bit of, something, in each step, and not try to go from the first step to the last step in one single stroke?
The issue I have is just trying to figure out, okay, what do I add next?
Right.
Like that's what's kind of gumming me up a little bit.
Yeah, well, that
But
the actual process takes just time and experience and exposure. But I'm just trying to explain the process. How to
works very well.
Okay, I'm glad that's working out, because that process is all about abstraction. Okay, I just want to spend a little bit of time to explain what is abstraction and why it is important in computer science when you're writing programs. Does anyone want to tell me what is abstraction, or to abstract something as a verb?
So, can I explain it in Java? I can explain it in Java.
Well, that's a very specific use of the word abstract. Abstract class. It's very technical. But what about the general meaning of that word abstract, or abstract, which is the verb?
It's like the high category level. Instead of talking about like, a Honda Civic, you can talk about a car.
Okay, that's good. Okay, so there was a hand over there.
Oh, it's like visualizing something just beyond the source code, like, you abstract it on the whiteboard, like, this function that exists, and it's this.
Okay.
And then
There's a little bit of that too, but in general, the word abstract means losing details. Okay, you're looking at a lot of several instances of something, and then you're saying, okay, this, and this are similar. Okay, I can see there's something similar between all three. What exactly is the similarity? And you lose the details. Okay, and it's something that we can naturally do. Okay, abstraction is something that humans can do. That's one of the wonders of our minds, is it can do that automatically. It's not something that you have to really think about it and do it. Sometimes we overdo it in situations that really should not be using abstraction. Okay, I'll give you one example, which can be controversial to some people. Profiling. Okay, law enforcement, profiling. Okay, so I'm not going to use an example involving race, color, of skin, or anything. I'm going to use a hypothetical example of smell. Okay, so let's say I'm a police officer, and for the past few times when I arrest someone, and I actually saw that person doing committing the crime, in every single instance, I smell that person is wearing a particular cologne. Okay, and that's consistent for the past 20 cases that I arrest these people. Okay, so when I go to 7-Eleven today, I walk in the store and I smell that same cologne again, and it's coming from this gentleman over here. What do you think I'm going to do?
Harass him.
I'm going to ask that person to step aside and empty your pockets and let me check whether you're hiding anything in your pockets. Okay, and that's profiling. What does that example, which is politically incorrect, has anything to do with abstraction in programming?
Kind of goes over I guess the root levels of what
It's abstraction at work.
Yeah.
Okay, it is abstraction at work. Except in programming, we are not abstracting, whether someone is committing a crime or someone is potentially a criminal. What are we abstracting? When we look at the examples, the concrete examples that we do by hand, what are we abstracting?
Methods and functions.
The methods, okay? What are we doing in each case? What are we doing on each row? Okay, the numbers change. Okay, the example changes. The array changes. The number we are looking for changes. But what we are doing in each step is not changing. So we are trying to extract that one single common thread out of all the examples in order to turn that into our programs. So that's what abstraction is and how it is useful in programming. Okay? Now, when abstraction is applied to programming, it is not natural. Okay? To some people, it is definitely not natural. Okay? You actually have to work to see the similarities between the steps that you have done by hand. Okay? But it does come easier, over time and over, just doing it more and more. Okay? Now, that also has a direct relationship to subroutines, because subroutines is usually a result of the application of abstraction. When you copy and paste in a program, you have to ask yourself, do I really have to copy and paste? Okay, because copying and pasting in programming is easy to do, it's very tempting, but usually it ends up with problems. Okay? And the problem has to do with whatever you're copying from. What if there's a bug there already before you do the copy and paste?
You're just going to keep the bug going later in the program.
Exactly, you're replicating that bug. Now, replicating the bug by itself is bad, but the worst part is when you're replicating it all over the place, it is hard to track down every single clone of the original code and the original bug.
Would it compound the problems too exponentially that it would create?
It doesn't do anything like that. It just makes it very hard to track. Okay, it's just really hard to track because what originally started off with one single bug that you only have to fix once, now you have n being the number of clones and copies that you have created from copying and pasting. Now sometimes it's not even a bug. Sometimes maybe it's just something that you want to add to the original logic. Okay? And now you have to do it to all of the clones. You have to find all the clones and then fix all of the clones. What if you miss one or two?
Problems.
There's no tool that can help you. So your program is now inconsistent. Sometimes it works right, sometimes it doesn't work right. And then it will really be hard pressed to remember what you did to the program, before you fix it. Okay? And subroutines can definitely help in that respect as well. All right, so the first thing we will do is to take a look at these links here, and I want to tell you which order to read it. You want to read the last one first. The reason is because it is the updated notes. It uses the notation and also terminology that is more consistent with the way I'm teaching the class. The other ones are not wrong. It's just that they're a little bit more fragmented and not as unified as the one that I point out here.
Are we going to trace our homework or?
Oh, that's right, the homework. Let's go ahead and trace the homework first. This is in topic 6. We'll trace the homework.
Homework
It won't
ended
take
up
long.
in topic 10.
Topic 10.
Oh, it moved down to topic 10?
Yeah.
Or I can just look for array 1.
Oh, it's in topic 9 now.
Oh, it's
Yeah, I moved stuff around a little bit too. Okay, so we'll go ahead and take a look at this one. This particular homework is tricky in the third iteration. The first iteration, not so much. The second iteration, not so much. But the third iteration is a little bit tricky. And is that the one that you have?
Yeah.
Okay, all right. Okay, so we'll go ahead and track this one down and find out what the trace is supposed to look like. Okay. Nope, that's the morning class, because I made the two homework assignments slightly different. All right, let's open this one. Yep, that's yours. Do you guys see the difference? No? I'm good at hiding that stuff. I don't really worry that much, with classes like this, but my next door colleague, has a lot of problems with people turning in homework assignments from past semesters. It's like opening up a time capsule. It's like, hey, the date of completion is about the same time in the semester, but 2 semesters ago, or a year ago, or 2 years ago. Oh, now I remember, that's the mom of this particular student. It happens a lot, unfortunately, in that class. Okay, so we're going to trace this particular program. As I said, the tricky part is actually in the third iteration, and I'll show you guys why the third iteration is particularly tricky. Line 1, no big deal. We are just initializing I to 0. Line 2, we have to evaluate the condition. I is 0 at this point. Bar A bar is 4 in this case because we have 4 elements in the array. 4 minus 1 is 3. 0 is less than 3 is true. We move on to line 3. Line 3 is now comparing A bracket I, which is A bracket 0, because I equals to 0, to A bracket I plus 1. A bracket I plus 1 is A bracket 1, because I is 0. So we are comparing 4 to 6. 4 is greater than 6 is false. Okay, no big deal. And then we get to line 8, which is adding 1 to I goes from 0 to 1. So the first iteration is not really tricky. The only thing I can say about the first iteration is you have to remember that even when the condition is false, you have to continue execution with line 8. Okay, but that part we have done it many times already, including several questions in the exam. Okay.
So it doesn't add the the A bracket I plus 1. I was adding the 1 to the 4.
To 4?
Yeah. So.
Okay, well, you're adding the 1 to the wrong place. Okay, this is also why we drew that picture, the tree thing, because the tree thing shows you, what operation has to be done first, right? So you have to kind of remember that. Okay, whatever is in the square bracket, you do that entire evaluation before you apply the square bracket operation, before you use that number to choose an element in the array. Okay. All right. So now we go back to line 2. Nothing much has changed. I is incremented. It is now 1. 1 is less than 3 is true. We go to line 2 again. But line 2 is now kind of, it's different. Okay.
Line 3.
Oh, line 3. Sorry. So on line 3, it's a little bit different now because we have a bracket I being a bracket 1. It has a value of 6. Compared to a bracket I plus 1, which is a bracket 2, it has a value of 2. 6 is greater than 2 is true. All right, it's true. So now we have quite a few things to do. We have exactly 3 things to do. Okay, but those 3 things, each one is just an assignment statement. So it's not really particularly tricky. And this is the second iteration. The second iteration is not the tricky one. So on line 4, we are looking at an assignment statement. It has the right-hand side, the left-hand side. We evaluate the right-hand side, change the left-hand side. Okay, very typical stuff. A bracket I plus 1 is the only thing appearing on the right-hand side. I plus 1 is 2 in this case. A bracket 2 has a value of 2. So the entire right-hand side is 2. We use 2 to update T, which is has its own column. So T has a value of 2 at this point. Are we doing okay so far? Okay. Moving on to line 5. Line 5 looks kind of nasty because we have the bracket notation on both sides. Well, don't let that bother you because we will do things exactly the same way. Okay. We will break it up into 2 operations, evaluate the right-hand side, and then we'll find out what to do with the left-hand side. The right-hand side is just a bracket I. I has a value of 1. A bracket 1 has a value of 6. So the right-hand side evaluates just a value of 6 in this case. We want to update it, we want a bracket I plus 1 to get updated to a value of 6. I is 1, 1 plus 1 is 2, so a bracket 2 is what we want to update. A bracket 2 corresponds to column G, so column G is the one that is going to get a value of 6. Then we move on to line 7. Line 7, once we can track down 4 lines, 4 and 5. I say one thing and I type another thing. Natural liar. The lie detector means nothing to me. But wait, lying means there's an intention. I don't even have the intention, which is even worse. I'll make a great spy, to spread, false information to whatever, right? I mean, it's like, Tech, how do we disarm this, nuclear missile? I think it's the password of 5661 when I actually am thinking about another number, right? Great. Okay, so on line 6, we use T to update a bracket I. Once we figure out what lines 4 and 5 are doing, line 6 is pretty easy because we are just picking up the value from T, which has a value of 2, and then we update a bracket 1 with it. A bracket 1 is column F, so now that guy gets a value of 2. We are done with the conditional statement. Moving on to line 8, adding 1 to I is now 2. Oops, see? It happened twice. It happened twice. We get back to line 2, and we reevaluate I is less than bar A bar minus 1. And for the last time, it is true because I is now 2, and bar A bar minus 1 is 3. 2 is less than 3 is true. We move on to line 3. And on line 3, a bracket I, now this is the tricky part. This really is the tricky part. A bracket I is a bracket 2, okay? That's not the problem, okay? We know that I has a value of 2. But what is the current value of a bracket 2? That is the tricky one.
6.
It has a value of 6 because we updated it in the previous iteration, okay? That is why it is tricky because most of the time people just look up the column from top to bottom and then go, oh, it's 2, 2. No, we just updated it. It is now 6. Okay, so now we can compare 6 to a bracket I plus 1, which is a bracket 3. It has a value of 5. 6 is greater than 5 is true. Okay, so this is the one tricky part. I'm not going to take off like a whole lot of points because of this, but I will take off some points because it is important to remember how to look up the values in the trace and make sure that you're only using the most up-to-date value in the trace. Okay, so now that we know this is true, we kind of know the drill already. So on line 4, we are copying a bracket I plus 1, which is the one to the right-hand side to t, and that would be 5 in this case. And on line 5, we copy the value of the one on the left-hand side to the one to the right-hand side. So we're copying 6 to, we're copying column G to column H basically. So this one gets a value of 6 now, and then we move on to line 6. We copy the value of t, which is 5 at this point, to a bracket I, which is a bracket 2 in this case. And we are done with the conditional statement. We move on to line 8. I gets incremented to 3. We go back to line 2, and this time the condition is false because I is now 3. Bar E bar minus 1 is also 3. So 3 is less than 3 is false. We get to post. We are done. Okay. This is actually one of the steps of bubble sort. Okay, because if you just kind of think about it, if you have a value, the largest value in the array will get pushed down to the end, okay, because it keeps exchanging it, okay, until it gets all the way to the end. If it picks up a larger value, it will move the larger value of the two, and push that to the end. And that's what bubble sort does, is it basically either bubble up or bubble down. In this case, it's actually bubbling down, sinking all the heavy stuff, to the bottom. Okay. Are there any questions about this trace? How many people got this completely and actually did not get tricked at all? Okay, very good. Good job. All right. So now that we got the assignment done, let's go back to subroutines. Oh. All right, so we are now going back to subroutine, and when we talk about subroutines, it might remind you of a boomerang a few times.
Didn't we have a updated order of notes? What was the order of the notes that you wanted to read us? That you wanted us to read that in?
Say again?
Because you were saying
Start
before
from
we
the
got
bottom.
it. Yeah, just
Oh
start
yeah,
from
read from the bottom
go up.
here. Yep.
And then just go up all the
Yep.
way, or okay.
Okay, so this is a better way to kind of organize the topics. You can see that I updated these notes about 3 years ago. That's one good thing about teaching algorithms. The same stuff. It doesn't change over time. I feel sorry for people who have to teach Windows. Windows 8.1 versus Windows 8, not the same thing. All right, so we'll go ahead and talk about this particular module, and I'm not going to read the notes here. You can read it on your own. What I'll do is I'm going to use some examples to illustrate what it means when we have subroutines, and also how do we trace programs involving subroutines. Okay, so we'll go ahead and use the spreadsheet to do it, and we'll start with a new concept. We can now define a subroutine. Okay, before this, we don't have the concept of a subroutine. Now we do. The syntax in pseudocode to define a subroutine is just define subroutine and then give it a name. Okay, I'll just give it a name of sub1. Okay, subroutine 1, and I'm not gonna do too many things here. The only thing I want to do in the subroutine is just to add 1 to x. And define sub, ending the definition of the subroutine sub1. Okay, that's it. That's how we define a subroutine, starting with define sub, giving the name, and then ending with end define sub to end the definition. It's really just pseudocode, so as long as I understand, this is the beginning and this is the name of the subroutine, that's the end of the subroutine, we're all good. Now we work on the actual program, okay, just like we usually do. So in this case, I would initialize x to a certain value, let's say 10, and I'm going to invoke the subroutine sub1, and let's have one more thing here. Okay, so we'll go ahead and x gets x times 2. That's it. Okay, this is the entire program. Okay, the first thing we have to understand is a subroutine, in this case sub1, or lines 1, 2, and 3, is really just a definition. But it doesn't do anything until it is invoked or called, okay, or triggered. Okay, there are many words to refer to the action of let's go to the subroutine and do whatever the subroutine is defining. Okay, but until such time that I say yes, go to the subroutine and do whatever it's telling you to do, don't do anything. It's just a definition. Okay. In other words, define sub1 and then the whole thing until line 3 is like an entry in the dictionary. Okay, it's just a definition. Maybe I'll refer to it, maybe I won't refer to it. It's just a definition. Are we doing okay so far? So line 2 doesn't get, we don't execute line 2 until we invoke it. We invoke the subroutine. Line 4 is now the first line that we are going to trace because it is the first line that is outside of the definition of a subroutine. So stuff inside the subroutine, we don't execute. We have to start execution with the first line that is outside of the definition of a subroutine. So that part has changed a little bit, okay, because we always start on line 1 before, and now we're starting on the first line that is not inside the definition of a subroutine. Line 5 is really the mysterious one, because line 5 is going to say, oh, okay, it's time to do whatever sub1 is, specifying. Okay, well, that part is not too hard to understand. We just go to line 2, start execution over there. When it's done, oh wait, when it's done, where am I going to go back to? We'll have to continue on to line 6, exactly, okay? Because I'm done with the invocation. I have to move on and do whatever is next to the invocation, okay? But how am I going to do that? I mean, how can we? Going there is not a problem, okay? Because sub1 has a name, and the invoke is spelling out the name of the subroutine that we're supposed to go to. That's not a problem. The problem is when we're done with sub1, how am I going to go back? How do I know that I have to go back to line 6? That really is the question. Okay. So we're going to trace this program. And in the process of tracing this program, we are introducing some new ideas, new concepts that is necessary to understand how subroutines work. Now, of course, somebody is going to say, attack, invoke sub1 is taking up one line. X gets x plus 1 is also taking up one line. So you're not saving anything here. Why do you even bother to make it a subroutine? Well, first of all, it is just an illustration. Okay, and that's why we have a really simple subroutine here. Typically, your subroutine will be much longer. Okay, not a single line. But some of the subroutines may only be a single line, and the purpose of the subroutine in those cases is abstraction. Okay, you're hiding the details of doing something, so that later on, if you want to change how it's done, you change only one place, and you're done. So there are subroutines consisting only of one line, and it is still meaningful to have those subroutines. But we'll get to those a little bit later. So right now, we can start with the tracking of the subroutine. We have line number. There are no conditions here, so I don't even bother with the comments column. We have one single variable, which is x, and it starts with an unknown value as my precondition of the entire trace. Fairly typical stuff, nothing really surprising here. And we start execution on line 4, as I said, because we have to start execution on the first line that is not inside a subroutine, at least in this class. This convention is not only for classes like this, when we use pseudocode, it is also true for scripting languages. So if you're dealing with Perl, PHP, many of the scripting languages are exactly like that. You can interleave subroutine definitions within the main program, but it will only start execution on the first line that is not inside a subroutine definition. So that is universal to almost all scripting languages. Okay, so line 4 doesn't do anything that's mysterious. It's just going to, initialize x to 10, and then we move on to line 5. At this point, we'll say line 5 doesn't really do a whole lot. I mean, all it's going to say is to say continue execution in the subroutine sub1. Okay, we can do that easily. So we continue execution on line 2. We don't execute line 1 because line 1 doesn't actually do anything useful. Okay, it's really just marking the beginning of a subroutine, but by itself it doesn't do anything. So there's nothing to trace on that line. Line 2 is a typical increment type of assignment statement. X goes from 10 to 11. And then we get to line 3. Line 3 doesn't seem to do anything useful. Now the question is, where do I go at this point? Well, we should go to line 6. And at that point, when we get to line 6, X gets doubled to 22. And now we are done, we get to post. Okay, so there's not a whole lot of problem here, okay? But something is kind of not right, okay? The part that is not right is, how do I know that I have to continue execution on line 6 after line 2? That part bothers me, okay? Because I don't know why it would continue. How does it know that I have to continue on line 6? So what I'm going to do next is I will copy the 2 columns here into sheet 3. So this way we can kind of contrast between the 2 sheets. And this time I'm going to say something and say, hey, you know what? When we execute line 5, it actually did something. Okay. So I'm going to insert 1 row here. When we get to line 5, it actually says, oh, you know what? I need 1 more column now. So we are dynamically allocating column C and say, I need to use column C for something now. Column C was not used before, but now that we are on line 5, I'm saying I need to remember something. I'm going to use column C, which is basically the leftmost available column at this point. Okay, you will hear that phrase again and again, the leftmost available column. And I'm going to give that column a label, which is return line number. Okay, instead of spelling out the entire return line number, I just use the abbreviation, so we don't use up too much space horizontally. And the return line number is basically a reminder to myself and say, when this subroutine is done, we should continue execution on that line. And which line number should I be writing down here?
6.
Line 6. Very good. All right. Cool. Now that I have column C doing something like this, after I execute line 2, I can now do something here as well. After line 2, now we get to line 3. Attack, you just said line 3 doesn't do anything. Well, now it does, because now that we have a notion of remembering where to return to, line 3 suddenly actually has something to do. In fact, it has 2 things to do. The first thing that it does is to look up the rightmost return line number that is still available. Right now, the rightmost return line number column is
6.
Column C, which has a value of 6, line number 6. So the first thing I do is to say, oh, I'm supposed to continue execution on line 6, and I copy the line 6 from here to here, just so that I know where to continue execution. That's one thing that you have to do. The second thing you have to do is to say, oh, but at this point, column C doesn't serve me any use anymore. Okay, I have just made use of the value that is stored in column C. It's no longer useful. So you have to basically say, well, we don't need that column anymore. We are deallocating column C at this point. And the way I represent deallocation is like this. It's basically the same text as the original one, except I will go to Format, go to, I cannot remember, it's Character, I think. So Format, Character. Okay, let's try Cell. Okay, Cell is the one. I use the strike through style to basically say this column is now not in use anymore. It is once again available. In this particular trace, doesn't matter because nobody else is going to use that column. But the next example is going to make use of it. Are we doing okay so far? Yep.
I'm just curious if instead of remembering line 6, you remembered line 5, would it like infinitely run?
That's why we don't remember line 5.
Okay.
That's exactly why. Because if you remember line 5, then it will continue execution on line 5, then we're going to invoke sub1 again and it will never stop. And that's why you always remember the line it's supposed to continue. Whatever line you have to continue to execute after the invoke statement is the line number that you have to remember. And sometimes it will take you to tricky places, like if the call or the invoke is deep inside a conditional statement that is nested and is the last statement in a branch, then you have to go pop all the way out and remember which line is supposed to continue execution on after the conditional statement.
So do you skip things like else's? And stuff like
Correct.
that?
We skip everything. It is as if you basically will be asking the question, after I'm done with the invoke statement, where am I supposed to go to continue execution? So if you have and if, else, and a bunch of stuff like that in between, it should not bother you because you just say, okay, the next line I'm supposed to go to is after the and if, so then you use the line number of that particular line after the and if. So we'll see some examples like that, but for the time being, we'll use something that is not that tricky. Okay. All right. So this is our first example. Okay. Definitely there are new concepts. Okay. The new concept is when you invoke a subroutine in the trace, you will do two things. One is to allocate the new column. The second thing is to remember which line you're supposed to continue on when the subroutine is done. When you get to end define sub, then in the trace you have to do two things as well. One is to look up the return line number, the rightmost return line number that is still active. Use the value stored in that column so you know where to continue execution. And then you deallocate the column and say this column is now once again available. Okay. So let's go ahead and change this program just a little bit and make it slightly more complicated. So I'm going to use I'm not going to actually save it, but I'm going to use this mechanism to basically replicate the program and keep the other one around. Okay, so what if I just have another invoke here and then have, let's say, another statement of x gets x times 3. Okay. Just so that we have something to do after the invoke. Okay, so here's my new program. I'm invoking sub1 twice in this case. So let's go ahead and trace this one, and that will be the last thing we do today. Okay, I'll just go ahead and remove these two sheets and use this one to start with. Okay, so once again, we have return line number. That clock is fast, by the way. It's only 8:13. And we have variable x here. So initially, we're only using one column. The line number column is really just for tracing purposes. But as far as the execution of the program is concerned, we're only using one column at this point, which is x. It starts with an unknown value. We start execution on line 4 because that's the first line outside of the definition of a subroutine. And now we go, excuse me, this is a precondition first. Then we work with the actual line here. Then we go to line 4. It gets initialized to 10. We go to line 5. This is boring stuff. We just did this before. We allocate a new column called return line number. And then we say, okay, which line am I supposed to continue after the invocation? Line 6. So you remember line 6 here. No big deal. And then we continue execution in the subroutine that you're invoking. In this case, it's sub1 starting on line 2. Line 2 is going to do its own thing, adding 1 to x. And then we get to line 3. At the end of the subroutine, remember we got two things to do. We look up the rightmost column that is called return line number. In this case, it's column C. It says we are supposed to continue execution on line 6. Fine, we'll continue execution on line 6 then. And then we indicate this column is no longer in use by using the strike out symbol like that. And then after that, we're done with line 3. We continue execution actually on line 6. Line 6 is doubling the value of x. X goes from 11 to 22. And then we get to line 7. We know how to do it on line 5. We should know how to do it now. So on line 7, we're doing exactly the same thing. 2 things we have to do. Allocate the leftmost available column. Which column is the leftmost available column? Column C, because we deallocated it. And that's why it is important on row 7 of the trace to indicate that column is now deallocated, because otherwise we'll keep using new columns, which will be a problem because we'll run out of columns eventually. So now we reallocate column C because it is actually available at this point again, and then we remember this time when the invocation is on line 7, where am I supposed to come back to when the subroutine is done?
Line 8.
Line 8, very good. Okay, so those 2 steps, is done. We can now continue execution in the subroutine starting on line 2. We just add 1 to x. X goes from 22 to 23. We get to line 3 again. And line 3 is doing the same thing as before. 2 things. One is to look up the rightmost return line number column. In this case, there's only 1 column that is labeled return line number. And it tells me I have to continue execution on line 8. Okay, so we say line 8 here so that we know where we're supposed to continue. And then after that, after we make use of this value, this column, once again, is no longer needed, and I'm deallocating it. Okay, so I'm deallocating it. It becomes available again. I continue execution on line 8. It is now tripling the value, so we have 69 in x, and we're done with post. Okay. So this is starting to illustrate something that we haven't seen before. Okay, we are dynamically allocating and deallocating columns. Yep.
What if we have a subroutine inside subroutine?
What if we have a subroutine invoking another subroutine?
Yeah, right.
Okay, because what you said can also be done in certain languages. You can actually define the subroutine inside the definition of another subroutine. But very few programming languages support that, Pascal being one of those. But what you actually meant is, what do we do when we're invoking a subroutine from inside another subroutine? That's a very good question. We are kind of running out of time. We got 2 minutes left, which is not enough to explain that. But I can go back to my notes. Okay? So don't fret, I got stuff that you can read. Invoking from a subroutine. So that's what you're asking. And that's the trace with explanation of what is happening when you do that. Now, in this class, I know you guys are anxious to get out. I want you guys to read ahead of me and try to read all the way up to and including invoking from self. In other words,
read up to 4. Read up to 4.
Yeah, but you can leave local variables, alone, okay? Because that's a kind of like a completely new concept. But we're going to talk about 3.4, hopefully in the next class. It's also called recursion, which is something that is.
Recursion, you said?
Yep, okay. Recursion, and that's an interesting concept.
Sounds like head smashing material. That's stress reliever. Sign. We post this on wall.